In geometry, a cube is a three-dimensional solid object bounded by 6 square faces, facets or sides, with 3 meeting at each vertex. The cube is the only regular hexahedron and is one of the 5 Platonic solids and has 12 edges, 6 faces and 8 vertices. The cube is also a square parallelepiped, an equilateral cuboid and a right rhombohedron. It is a regular square prism in 3 orientations, and a trigonal trapezohedron in 4 orientations. The cube is dual to the octahedron. It has cubical or octahedral symmetry. Orthogonal projections. The cube has 4 special orthogonal projections, centered on a vertex, edges, face and normal to its vertex figure. The first and third correspond to the A2 and B2 coxeter planes. Spherical tiling. The cube can also be represented as a spherical tiling, and projected onto the plane via a stereographic projection. This projection is conformal, preserving angles but not areas or lengths. Straight lines on the sphere are projected as circular arcs on the plane. Cartesian coordinates. For a cube centered at the origin, with edges parallel to the axis and with an edge length of 2, the Cartesian coordinates of the vertices are, while the interior consists of all points with -1 less than xi less than 1. Equation in R3. In analytic geometry, a cube's surface with center and edge length of 2a is the locus of all points such that formulae, for a cube of edge length, as the volume of a cube is the third power of its sides, third powers are called cubes, by analogy with squares and second powers. A cube has the largest volume among cuboids with a given surface area. Also, a cube has the largest volume among cuboids with the same total linear size. Doubling the cube, or the Delian problem, was the problem posed by ancient Greek mathematicians of using only a compass and straight edge to start with the length of the edge of a given cube, and to construct the length of the edge of a cube with twice the volume of the original cube. They were unable to solve this problem, and in 1837 Pierre Wansel proved it to be impossible because the cube root of 2 is not a constructible number. Uniform colorings and symmetry. The cube has 3 uniform colorings, named by the colors of the square faces around each vertex. 111, 112, 123. The cube has 3 classes of symmetry, which can be represented by vertex transitive coloring the faces. The highest octahedral symmetry O has all the faces the same color. The dihedral symmetry D4H comes from the cube being a prism, with all 4 sides being the same color. The lowest symmetry D2H is also a prismatic symmetry, with sides alternating colors, so there are 3 colors, paired by opposite sides. Each symmetry form has a different with-off symbol. Geometric relations. A cube has 11 nets. That is, there are 11 ways to flatten a hollow cube by cutting 7 edges. To color the cube so that no 2 adjacent faces have the same color, one would need at least 3 colors. The cube is the cell of the only regular tiling of 3-dimensional Euclidean space. It is also unique among the Platonic solids in having faces with an even number of sides and, consequently, it is the only member of that group that is isonahedron. The cube can be cut into 6 identical square pyramids. If these square pyramids are then attached to the faces of a second cube, a rhombic dodecahedron is obtained. Other dimensions. The analog of a cube in 4-dimensional Euclidean space has a special name, a tesseract or hypercube. More properly, a hypercube is the analog of the cube in n-dimensional Euclidean space, and a tesseract is the order 4 hypercube. A hypercube is also called a measure polytope. There are analogues of the cube in lower dimensions too. A point in dimension 0, a segment in 1 dimension and a square in 2 dimensions. Related polyhedra. The quotient of the cube by the antipodal map yields a projective polyhedron, the hemicube. If the original cube has edge length 1, its dual polyhedron has edge length. The cube is a special case in various classes of general polyhedra. The vertices of a cube can be grouped into two groups of four, each forming a regular tetrahedron. More generally, this is referred to as a demicube. These two together form a regular compound, the stello-octangular. The intersection of the two forms a regular octahedron. The symmetries of a regular tetrahedron correspond to those of a cube, which map each tetrahedron to itself. The other symmetries of the cube map the two to each other. One such regular tetrahedron has a volume of 1/3 of that of the cube. The remaining space consists of four equal irregular tetrahedra with a volume of 1/6 of that of the cube, each. The rectified cube is the cube octahedron. If smaller corners are cut off, we get a polyhedron with 6 octagonal faces and 8 triangular ones. In particular, we can get regular octagons. The rhombic octahedron is obtained by cutting off both corners and edges to the correct amount. A cube can be inscribed in a dodecahedron so that each vertex of the cube is a vertex of the dodecahedron and each edge is a diagonal of one of the dodecahedron's faces. Taking all such cubes gives rise to the regular compound of 5 cubes. If two opposite corners of a cube are truncated at the depth of the 3 vertices directly connected to them, an irregular octahedron is obtained. 8 of these irregular octahedra can be attached to the triangular faces of a regular octahedron to obtain a cube octahedron. Relational sets of polyhedra and tilings. The cube is topologically related to a series of spherical polyhedra and tilings with order 3 vertex. Figures. The cube octahedron is one of a family of uniform polyhedra related to the cube and regular octahedron. The cube is topologically related as a part of sequence of regular tilings, extending into the hyperbolic plane. 4 p equals 3, 4, 5. With dihedral symmetry, DIH4, the cube is topologically related in a series of uniform polyhedra and tilings 4.2n, 2n, extending into the hyperbolic plane. All these figures have octahedral symmetry. The cube is a part of a sequence of rhombic polyhedra and tilings with n3 Coxeter group symmetry. The cube can be seen as a rhombic hexahedron where the rhombi are squares. The cube is a square prism. As a trigonal trapezohedron, the cube is related to the hexagonal dihedral symmetry family. In uniform honeycombs and polychora, it is an element of 9 of 28 convex uniform honeycombs. It is also an element of 5 four-dimensional uniform polychora. Cubical graph. The skeleton of the cube form a graph with 8 vertices and 12 edges. It is a special case of the hypercube graph. It is one of 5 Platonic graphs, each a skeleton of its Platonic solid. An extension is the 3-dimensional Kary Hamming graph, which for k equals 2 is the cube graph. Graphs of this sort occur in the theory of parallel processing in computers.